first of these two formulas is something that you've already seen. When we said that the slope of the velocity time graph was acceleration, this is exactly what we were talking about. It's the rise of the velocity time graph over the run, or change in velocity over change in time. This formula is a little bit new looking. What this thing says is that if I have a situation where I'm changing speeds, we can use a really powerful technique called averaging of speeds, where as long as somebody's traveling smoothly from one speed to another, so like our policeman did, if we go from one velocity to another velocity and we do it in nice even steps, then this is a technique that's going to work for us and be really a powerful problem-solving tool. So what we're going to do is we're going to see how we link both of these together with the graphing stuff that we were just talking about to give you some really strong problem-solving skills. So here we go. Now in this problem, what we're looking at is a little kid speeding up a ball bearing from speed here to speed there in a certain amount of time. And in this problem, all they're asking for is what acceleration does the metal ball experience. So in a velocity time graph, the real quick sketch would look like this. The ball bearing starts at 0 speed, ends up going 100 meters per second, and they told us that the amount of time that that took was 0.3 seconds. So I could use a couple of tricks. I could use the slope of that line to figure out acceleration, or what I could do is use the formula acceleration equals change in velocity over change in time. And so let's just go have at it. Change of velocity is v2 minus v1, so you have 100 minus 0 meters per second over change in time, 0.3 seconds, and that turns out to be really quick. You have 333 meters per second, watch for it, over seconds. Boom. And that's how you do that one. Very straightforward. Acceleration equals change in speed over change in time. In this problem, what we're looking at is a situation where Felix Baumgartner, who's tackling the human speed record in free fall, has a lot in common with that ball bearing that we just looked at. When you drop both Felix and the ball bearing, they both change their speed in exactly the same way. So in this one, what we've got is a velocity that he begins with, a velocity that the ball bearing ends with, and an amount of time. And so this is exactly the same kind of problem that we had a second ago. What we're going to do with this one is take a look at the formula acceleration equals change in velocity over change in time, and v2 minus v1 is minus 29.4 minus 0 meters per second, all over the change in time of 3 seconds. And what that gives us is actually a negative acceleration of negative 9.8 meters per second, and there you see it again, per second. And that is the acceleration of free fall. Now you'll see it a lot of times in physics problems when we discuss free fall. We round that to minus 10 meters per second. But the thing to just think about for a second is that that minus sign, like we were talking about, that means direction. That doesn't mean that you're always slowing down when you're falling. In fact, Felix Baumgartner and ball bearings don't slow down when they fall, they speed up. But that minus sign is going to mean that he's falling in the minus direction. So that probably meant that we thought that down was the minus direction when we set that problem up in the first place. So you'll see more of that later. Not to worry about it now, but you'll see more of it later. So the McLaren F1 is one of the fastest production cars on the planet. And we have these few tidbits of information here. We have a starting speed, we have a final speed, and we have some time that goes by. And what we're going to use this problem to do is to set up the techniques that you want to use on motion problems for a long time to come. So you're going to see us work step by step through some really strong problem-solving strategies. So what they're asking us to do is really three things. Draw a velocity time graph for the motion, and then figure out acceleration, and then how far this car travels. So away we go. So if we look at this problem and write down a velocity time graph to begin with, the way that would look would just be like this. we have a car that's speeding up, so from 0 speed to a top speed of 45 meters per second, so that the whole thing would take 6 seconds to do. And then we could use those two graphing techniques we just talked about if we wanted to. We could find the acceleration by finding the slope of this line, and we could figure out the displacement, or how far the car traveled, by using the area under the graph trick. And so the way that would look would be, we'd recognize that this was a triangle, and we'd color it in maybe, but we would use 1/2 base times height to figure out the displacement of the car. What we're going to do in this situation, though, is show you step by step how to use algebra as a problem-solving tool. And this technique turns out to be really popular with a lot of students. So the point of the velocity time graph, come back here, the point of the velocity time graph is that it gives you a clue about what's going on in problems, even when they're really complicated. So this one may or may not have been in your mind, but if I were able to draw that graph, and you should always be able to draw that graph to understand what's going on, just basically in the problem, then what you can get is this sort of information. I have velocity 1. What was the first speed the car ever had? So that was 0 meters per second. V2 was the second speed that they gave us. With that was 45 meters per second. And in this problem, they gave us that the time was 6 seconds. Just based on these two things, I should be able to use the two algebra formulas that we talked about a minute ago to get into this question. So to start with, V average is equal to V1 plus V2 over 2. So that's 0 plus 45 meters per second over 2. And that's equal to 22.5 meters per second. The next thing that you might be able to get off of this would be, what's the change in velocity? So I know change in velocity is V2 minus V1, so that's going to end up being 45 meters per second. So the next trick we're going to use is those two formulas to put this all together. So to answer question 1, what we're going to use is acceleration equals change in velocity over change in time. And we just wrote down that change in velocity was 45 meters per second. Change in time is 6 seconds. And we end up with an acceleration of 7.5, watch for it, 7.5 meters per second every second. So again, that's meters per second per second. The displacement is going to be something we can find, because now we're going to use average velocity times time. So even though the car was traveling a whole bunch of different speeds, we're going to use the fact that the middle speed right here, the average speed, is going to cover for all the time that the car was traveling. So 22.5 meters per second times 6 seconds, and we end up that the car travels 135 meters. So there you go. That's one totally solved physics problem done in two different ways. The last example we're going to look at is one in which we're going to take the velocity time graph and use the fact that it's a flexible problem-solving tool to deal with a question that's one of the most challenging kind, and that's one where we don't have all the information that we need. The thing that you're going to learn to look for is that in a physics question, if they don't give you time, then they're setting up a pretty challenging situation. So in this story, we have a driver of a car who's cruising at a pretty fast rate of speed. That's probably about 55 miles an hour, and sees an animal in the road maybe 125 feet in front of him. So that's not a really big distance when you're driving fast. But they tell us something about the way the car can slow down. So we notice that they don't give us time, and so it's a good example of a problem where we don't have everything that we might like to have. So what we're going to do is use the velocity time graph as a way of showing people that we have a clue. And so that's the first thing we're going to start with. So, like I always do, start with a little velocity time graph, and I use the common sense that I have from reading the problem to know that this problem is all about a car slowing down. And even if that's all I knew, that's still enough to get me going in this problem. So if I know the shape of the velocity time graph, that it's a car slowing down, I can get started and I'll be able to do math pretty quickly as a result. The first speed they gave us was 27 meters per second, and what I want to do is follow that car until it's stopped, because I know that when that car is stopped, if it's 0 meters per second, then the car has no chance of hitting the moose anymore. And what I'm also going to do is use the fact that this number right here is an acceleration and that it's equal to the slope of the velocity time graph, I'm going to use that information to help me uncover the thing that's really crucial. And what I'm going to use it to use, namely to get at, is the idea of time. So let's go ahead and check that out. So from our graph, we know that the first velocity, come back here again, first velocity of the car was 27 meters per second. And we know that the second velocity of the car was 0. And we also knew for a fact that the acceleration of the car was minus 8.5 meters per second every second. And this is where decision making comes in. I have two formulas that I can use. I have distance equals v average times t. So that's one of the formulas. And I also have acceleration equals change in velocity over change in time. And that's the second formula. And in this case, the one that I'm going to use is I'm going to zero in on this one, because usually, as a good strategy, the first thing I'd want to do is try to find out time if I can. And I have enough information in this problem to figure out what delta v is. And they also tell me for a fact what the acceleration of the car is going to be. So that's the thing that I'm going to get after. So just clear a little space here. And what I'm going to do is take the information that I've got and go ahead and do some algebra. So I know if delta v over delta t is acceleration, that tells me that delta t equals, I'm going to cross multiply here, and I'm going to bring the acceleration down. It's going to be delta v over a. So if I go ahead and plug in, the delta v of the car is minus 27 meters per second. It's going to lose speed at 8.5 meters per second, or around 3.2 seconds. So now that I've got that information, I can do the really important stuff, which is to go ahead and complete my velocity time graph. And let's get rid of this guy and that guy. And so here's what my velocity time graph is going to look like. I've got 27 meters per second slowing down, that whole thing taking 3.2 seconds, and I can finally use the last formula, d equals vt, to figure out how far the car actually travels. And inside that, by the way, there's a big hint. In these kinds of questions, which are a lot of times involve decision making, the best hint is if they give you the distance, to pretend that you don't know that distance and actually save it for the last minute and solve for it, because you're going to end up with a real distance. So the thing that I want to do then is use my formula d equals v average times time, and v average we know is going to be 27 meters per second plus 0 meters per second divided by 2, and then times the 3.2 seconds that I just found. And when I go ahead and crank that out, I'm going to find out that that's about equal to 42, maybe 43 meters. So the answer to the question is going to be that, yeah, there is actually a collision between the car and the moose. The car would like to continue another 10 feet through the moose, but probably that collision happens down in this part of the graph where the speed of the car is going to be very low. So probably everybody walks away from this accident, the moose included, and everything's okay. So what you see there is how to handle the velocity time graph to set up and solve even the more complicated kinds of questions where there might be things that we don't know. So there you go for now. What you should be able to do is to use this tutorial in combination with the answers that we've provided online through the portal to go ahead and set up and solve the beginning worksheets in the 820 series, so 821, 822. So we'll see you soon, and keep on thinking physics. Bye-bye.